Hey, what's going on, guys? Games here. So in this video we'll finally create a 3D projection for our two-dimensional raycasting algorithm. So if you're interested, without further ado, let's actually start. Okay, so let's start by running the code from the previous video basically. So here is what we have. So we have a two-dimensional space and we have the raycasting algorithm being implemented. So what we currently need to do is to handle the updates of the background for our 3D projection. So as you can see here, it's not being updated, so we don't really want that sort of behavior. Okay, so so here we'll say update 2D background, and here I say update 3D background. Okay, so we would be drawing the rectangles just like that, but okay, so let's take the color of 100s, 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 and starting from, so we should take this half width. Do we have the half width? Well, okay, let's take just the screen height. The idea is, well, I would even better take the constant just to avoid any confusion. So we just want to draw to on the right part of the screen, let's say. Okay, so 480, so that's the starting coordinate. And here we want the screen height divided by 2. Okay, so let's have a look. Should have the half. Okay, so here is our floor. Great. So now on the floor we have an update. So say like it just doesn't stuck. Yeah, that's because I walked through I've exceeded the bounds of the map. That's the reason for the error. But we'll implement the collision detection, and that won't be on the cards any longer. Okay. And so this was the floor, and this is gonna be the ceiling. And for ceiling, let's make it lighter like this. Okay, so yeah, now we got the floor and the ceiling. Well, probably yeah, I think this is okay. Yeah, I think this is just kind of fine. Okay, guys, so now a bit of a theory of how we're going to be building our 3D projection. So the number of rays is equal to 120, and every time the ray hits the surface, so when the ray hits the wall, here we're going to be drawing rectangles like this. And now the closer we have this ray hitting the wall, the bigger our rectangle would be, and the further it goes, the smaller our rectangle would be. So it would be like a perspective effect. So that's kind of pretty. So the entire 3D projection is just a matter of drawing rectangles, and that's pretty it. So before anything else, let's define one more constant. So bear in mind the fact that we have the number of rays not being equal to our resolution. So our actual screen width is 480. So let's just, because we only use the half of the screen. Okay, but the number of casted rays is only 120. So we need to scale we need to scale our screen height and the rays. And I just want to create the scale variable here, which would be equal. So let's say screen width divided by 2, and well, actually I could have just say 480, but yeah. And I want to divide this by casted rays by 120. Okay. Now the next thing, as I've been already mentioning, we need to define the wall height depending on how far the wall is from the viewer's perspective. So The further the wall would be, the smaller it would be. The closer wall to the player, the bigger wall height. The bigger wall height will have. So in the cast raise function, so here we want to calculate wall height. Okay, so wall height would be, and there are many different ways of how that can be calculated, but I personally prefer just trial and error method, and just to make sure that the height of the walls is just good enough, I take some random constant. Well, it's not really random constant. Well, I'm using 21 thousandths divided by depth plus this little small number. So the idea is just to avoid the division by zero error. And now we want to draw 3D projection, but literally projection, let's say rectangle by rectangle, rectangle by rectangle. So here pygame dot draw, so want to draw to the window. At the moment, let's make the color just white. We'll add shading in the next step. And now the starting point, so this would be 480. I just use this, or we can use the screen height. If you don't divide the screen, you don't need this really, but I need this screen height plus, and here I need to say array multiplied by our scale. Okay, yeah, so probably just put it down here. And now we need to take the half height of our screen height. So screen height taken divided by 2. Screen height. Screen height divided by 2 minus wall height. Wall height divided by 2. So here we have the x coordinate, like x offset, y offset for where to start drawing our rectangle. So let's say this is the window, so like how many, so what are the initial coordinates, and the next two parameters are width and height. So width is going to be equal to scale, and height is going to be equal to wall height. Wall height. And if I did everything properly, it should now, okay, it should now draw some, okay, walls. Okay, scale, just a bit typo. Scale. The moment of truth is about to come. Okay. Module. Yeah, obviously we need to draw a rectangle here. Okay. And can you believe it, guys? So we now have our walls, but here are some things that we want to fix. So we have the eye fish effect, which is not really that great, so we need to fix that. And also we need, it would be nice to add some lighting, or it would be better to say some shading. So the wall here would be light, and the wall here would be dark. So in order to do that, we need to adjust the color depending on depth. So I'm just thinking where it would be better to, yeah, let's define the color here. So wall shading, and color would be equal to white divided by depth plus some small constant. Okay, and now here instead of white we can have our color, and color, and now it should give some shading. Yeah, it's a bit too much, I would say, so let's fix this slide a little bit. So let's say depth plus depth multiplied by depth. Okay, I'm sorry. What have I done? Obviously we need to multiply here, not add. Okay. Yeah, now it's much better. Okay, invalid color argument. Oh, and probably yeah, now this is fine. So we have the shading being enabled now, so the further walls stand, the darker they are, but we still have this horrible fish eye effect. So you see, like the square, this walls are getting like rounded, and just to give you an idea why is this happening. So the distance from here to here is bigger than distance from here to here, or from here to here, or from here to here. And you remember that we do scale our rectangles representing the walls depending on depth. So the further we have, the longer array we have, the smaller our rectangle representing the wall would be. And let's say here, in case of the perspective, it seems to be working nicely. See, like we have big rectangles here, and then like they go in smaller and smaller. Okay, but when we just have a look at the wall, it's not really that great. So again, a bit of a math to fix this. I have no idea how the math works in particular, but the idea behind it is that we make all the rays of kind of like the same depth when we look at this wall. So we can simply say fix fish eye effect, and just by saying depth multiply equals by math dot cosine. Don't ask me why, I have no idea. And player angle minus start angle. And if I did everything properly, it now should fix this fisheye effect. But at the same time, we define color before fixing this. So if we define the color after, the lighting would be a bit too poor. But in this case, we have a lighter wall in the center and like shade into the dark when it comes to the sides. If we swap this lines of code, the shading would be flat. So I think it's better to keep the the coloring, like the shading, before fixing the fish eye effect. So let's have a look whether it works actually. Yeah, and it does work. So you see, like we have light in the center and going dark to the sideways. So this is the exact effect I actually wanted to achieve here. Okay guys, so this is kind of it. So just a few more adjustments. So one of the issues is that we can walk through the walls, and yeah, not only actually, no, it's not exactly. So it's like we stuck at the wall. So before adding the collision detection, we need to fix this being stuck at the wall. So this happens in case, oh my god, this happens in case if the wall height is getting greater than the screen height. So to fix this, so let's say fix stuck at the wall. So we can say if, no, it's not here, sorry, it should be here. So if wall height is greater than the screen width divided by 2, or let's say no, then the screen height. This is okay. In this case, this is okay. In this case, I want to say the wall height equals to the screen height. Okay, so let's have a look whether it gets fixed. Okay, yeah, now this is just fine. So you see, like, we can now move through the walls, which is a little bit odd. So let's try to add the collision detection. I'm sorry it's going a little bit laggy because of my video recording software. So we'll add the frame per second being printed in the corner of the screen, I believe. Yeah, just to make it just to have an idea of the performance of this sort of a thing. Okay, so let's add collision detection. So it would be very similar to what we've been doing here when we've been detecting the collision of the ray and the wall. But in this case, instead of using the target X and target Y, we're going to be using the player X and player Y. So we can grab this code, copy, and then go into the very beginning of the loop. So before anything else, here, so here we get the row and the column for the player X and player Y. So player X and player Y, and the square, and here player hits the wall, or just a collision detection. So in this case, we want to do the opposite to what, so sorry, just the indentation seems to be a bit wrong. We need to do the opposite what we've been doing here. So copy and paste, but we want to say minus, and minus literally dropping back. So let's have a look if this works. Okay, so you see here on the diagram, it's really fun to see, like we just not going any further. Okay, so now we have our collision detection. However, we still can walk through the walls if going backwards, and this is a little bit unfortunate. So let's fix that as well. So I'll add a new, so say moving direction flag. So let's say forward equals to true. Okay, so want to do this only if forward, and otherwise we want to do the opposite. So copy, paste, and plus equals, and now when we go up, when we press the up key, we need to say forward equals to true, and here we want to say forward equals to false. Okay, so now go in there and now go in here. Okay, so now go in here, not exceeding the bounds when going backwards as well. Yeah, this is pretty nice. Okay, So yeah, the very last thing to consider is to add the frames per second. So if I don't use the video recording software, it goes 30 at very least 30 frames per second. Even though the algorithm is not optimized, which is really good, it might drop down because of the video recording software working. But anyway, so just let's put our clock here. Okay, so here we want to get frames per second. Well, actually just paste the code in because nothing really interesting here. So we're getting the frame per second, converting it to string, then initializing the font, then creating a surface for our font using the font.render, and then we're split the surface to the main window. That's pretty it. So well, let's call this one FPS surface just to make it clear, and FPS surface here. So let's just bring some commentary. So here we want to initialize the font. Say pick up the font. Okay. Here we want to create font surface. And here we print FPS to screen. We'll need to play around with the coordinates, so this should be screen width divided by 2. Okay, plus, I think plus, well, sorry guys, you can't even imagine how bad in math I am, so yeah, let's go trial and error here. Yeah, after completing this tutorial, I've realized that 3D graphics is not really for me. Okay, so yeah, hold on a sec. So this should be white. Okay, I just can't get why it doesn't print. Okay, yeah. Now prints it right over in here. Okay, let's just give some constant. Let's give a probably that was the floating point number. That's the reason. I might be wrong though, but okay. Yeah, now this is fantastic. So we got the frames per second right over in here. Okay, so yeah, it's miserable number currently, and by the way, when we have in the counters, it's bigger because yeah, it's just faster to calculate when the ray hits the wall. So here as well, there's the reason why in the old school games there wasn't much of open space, so it was all within like walls, some rooms, like in Wolfenstein 3D. Yeah, but again, like, if I just turn off my video recording software, it should be around 30 frames per second, which is exactly, so the eye distinguishes 24 or 25, I'm not sure, frames per second. So everything that goes below the 24 frames per second we can't see as a delay, but everything goes higher than 25 frames per second we can distinguish that using the human eyes because it's not capable of seeing that difference. Okay guys, I think this is it from my side. Now at the very end, just a few words on like the summary of this kind of project. So as I've been mentioning in the very beginning of the series, I've been through really lots of tutorials, but I didn't really find one that would be explaining not how the math works, but how to bring things all together, basically. And one of the issues, so let's say the next step would be, it could be to add some textures, and I need to say that I've been playing around with adding textures, and I did even manage to add some textures, but the result, but the overall result was horrible. So I can't share that because that just looks awful. It works in theory, like it does draw the textures on the walls, but I just don't really like how that works. And the problem is, well, apart from the slowing down, so just the general idea. So if we want to draw the textures, then instead of blank kind of like rectangles, we want to bleed the images. So we need to calculate the texture offset, and then we need to scale that. So eventually it gives an illusion of as if texture was kind of printed on the wall. But yeah, so first of all, it starts getting slower, which is a bit of an issue on the one hand, and on the other hand, all the tutorials I've been through, when it comes to rendering textures, they already started using a more sophisticated algorithm for the raycasting on its own. So I just want to say, well, I was wondering, is this possible to apply the textures using this most primitive raycasting algorithm we've implemented here? Yes, it's possible, but I don't really like how the result looks, so I'm not going to be doing a tutorial about that. Probably if I put some more time and effort, it would be better, but even if the texture would be pixel perfect, still the frame per second rate is dropping down, which is not the case. So if we want to add sprites later on, it would be even more miserable, so it's not the way to go. So I just want to give you an idea that if you want, say, 3D shooter, even like in Wolfenstein 3D style, in that case the raycasting algorithm itself should be done in a different way. So the output would be exactly the same, but the way how this ray is being casted is different. So it involves some extra math, which I can't really understand because I'm too dumb in math. And again, like, it just, like something you can do some range of things quite easily, but when it comes to, well, for me personally, when it comes to math, and I believe that if I have such big troubles with raycasting, then with the real 3D graphics, I would just die there. So I've realized after completing this tutorial, I've realized that 3D graphics is not for code keen, definitely. So it's better for smart guys who understand the math. And the most important thing, it's not even again, like, it's not the matter of understanding how exactly the math works. It's just the matter of a never-ending calculation. So like, say you want to add some textures, you need to put this into your mind, you need to imagine, so where you have this square, where you put this on the screen, how you calculate the offset, you need to have in mind the two-dimensional image, the three-dimensional image, and rotate this in your head back and forth in order to get an idea how this actually works. And for some people this is a very natural process, but for me personally it's a complete hell. So that's the reason why I don't really want to proceed with this any longer. And again, like, so my initial goal was to make the easiest possible raycasting engine that is extremely easy to understand how it works, and the one that you can try it with your hands, like get hands dirty to have an idea like how in particular it works. And I think that this state with the 3D projection and the simple shading and the two-dimensional map, which is the essence of the entire algorithm, like what's actually happening under the hood, I think this is pretty it. This is really enough to demonstrate how the entire concept is working. So I'm sorry for talking too much. This is from my side. Thanks for watching. Thanks for following this tutorial series. Until the next time, and take care.